Oh, and by the way, we can still do things like cross wires. So here's a set of cells in the Songline processor. And we could have a signal traveling like this from left to right. And we could still take a signal from this K side and send it into here, bring this down here, and this can go into this side because we have data flowing in both directions, and that can cut across and come through the K side and come out here. And so we have this point connected to this point, and we have this point connected to this point. So we can still cross over and not box ourselves too painfully into a corner where we can't transmit signals. You have all the usual routing issues to deal with planar routing, but it's not necessarily more restrictive than four-sided cells. All right, so let's look at the following function. So here's a cell. Here's another cell. Here's a third. I'm going to take an input over here. I'm just going to call this in. And this is going to come into here. And this is going to be an input that I call load. And that's going to get routed into the southern input on here. All right, let me talk about this function separately. This cell, the second cell over here, is going to route its left input back to its left output. So what does this cell here do? It does the following. It says write equals, and it can be one of two things, based on the value coming into the K line. So if K is less than 2.5, or K is bigger than 2.5. So if K is bigger than 2.5, the output to the right is just going to be whatever's coming in on the left. And if K is less than 2.5, the output to the right is going to be whatever's coming in on the right. And we're also going to take this value and send it out to its K side, and we'll call this Q. All right, what have we done? We've just built a simple D flip-flop. So when the load line is low, this input is 0 volts. This input down here is 0 volts. This function is simply taking whatever's coming from the right and sending it back to the right. Whatever value you have stored here, whatever value you're seeing on Q, you're going to continue to see, and changing the input has no effect. But when the load line goes high enough, when load is bigger than 2.5, this changes behavior, and now the output to the right is whatever is coming in on the left. And at that point, whatever value you set on the input, you see coming out on the Q output. And when you drop the load line again below 2.5 volts, that last value you saw will now get recirculated back by this and will be trapped between these two cells. So it acts like a D flip-flop, but it's actually more like a sample and hold. When this input gets sufficiently high, the input line here gets loaded into this memory circuit. And when the load line drops, the value coming in at the point when the load line drops below 2.5, that value is stored in here. So it holds that input value until you raise this input again, which says read another sample. And while you're reading a sample, the Q output tracks your input. So it's like an analog flip-flop, which is an interesting notion. We can do lots of things with that. Let's go ahead and look at what the code would look like for this, and we'll talk more about code when we go into the simulation tools in another set of videos. But let's take a quick look at how we might code this up, and then we'll go from there and talk about C mode. All right, the simulation tools let us specify a description of what we want inside each cell, what functions we want each cell to perform. And we do that in a plain text file. That file is compiled using some of these tools and then loaded into the simulator as a binary image, and the simulator goes ahead and mimics the behavior of the songline processor. And there's a couple of different varieties of simulation. There's software simulators, which simply put up a graphical interface and let you change the inputs using sliders and look at the outputs on some bar displays. But there's also one version of a physical songline processor. And in this version we have 4 input channels we can control with these knobs. And we have 6 output channels, and we can choose which one we want to look at and see the output voltage on a meter. And there's also connections we can make on the back to external input and output sources, and those will be available for display through whatever we hook up to this. This whole thing talks to a computer through a USB port, and the computer runs the actual simulation engine. This is really just the I/O unit. So we'll play with this in another video, but let me show you how we might write the code for this particular circuit to implement a D flip-flop. So the code looks a lot like C because we actually punt to the C compiler to do some pre-compilation of this code. So here's how we could define this circuit. We use a command called set_tt. And set_tt does the following. We give it a row, a column, an output, and an input. So let's set up this cell's truth table. So we would say something like set_tt, and this is row 1, column 0, and we want to set the K output, and in this case we just want it to be equal to whatever value is coming in on the left, and that's just L-val. And that specifies this cell's behavior. This cell up here, we need a pair of equations. Set_tt, so this is row 0, column 1, 0, 1, and we're going to set its left output to be whatever value is coming in on the left. And set_tt 0, 1, and we want its K value to also be whatever is coming in on the left. So that mimics this piece of the wire. Now, this cell's function is contingent. It's contingent on the value of K. And we have 64 bins, so our inputs are between 0 and 63. So we could actually write K is less than or equal to 32, or K is bigger than 32. And so we can write the following: if K is less than or equal to 32, set the TT of 0, 0, and we're setting its right output to be K is less than or equal to 32 to be just the R-val, else set TT 0, 0, R to be the L value. And there's a program that describes our 3-cell songline circuit. Now, it's one of these things where if you don't think about it too deeply, it makes sense, right? This if-then-else statement is coding our intention here, which is if the K input is too small, then we set the truth table like this. If it's too large, we set the output like this. The fact that this if statement is changing the function that's going to be compiled in here can seem a little weird because it's got a blurry distinction between runtime and compile time. That's not surprising. If you've studied the cell matrix, you know that that blurring of runtime compile time is sort of endemic in the whole cell matrix architecture. And I think that's what we're seeing here, is that this is code we're going to compile, but the code that's compiled as a result doesn't contain an if statement, right? The code that's compiled is such that we get this effective behavior. If K is less than 32, the stored function looks like this, otherwise it looks like this. Don't think about it too much, unless you like that kind of thing. So this is the code for a D flip-flop sample and hold circuit. There's also a configuration file that goes along with the compiled binary for this, and that configuration basically maps inputs and outputs to particular channels, so that if we're looking at the behavior of the circuit on something like this, we can say let's map the input to channel 0, map the load to channel 1, and now we can use this knob labeled 0 to control the input, this to control the load line, and we could say let's put the output on channel 1, and by putting this on channel 1 we can see the output on the meter. So we'll actually do that demo in a few videos, but let me talk about C-mode behavior next.